So, today we are going to talk about a form of metaprogramming. And I want to say right away that what we're going to talk about today is not going to be the only metaprogramming facility in this language. We're going to do something that's like templates in C++, but way better. However, you could imagine a style of metaprogramming for this language that doesn't involve template kind of things. For example, in previous demos, I have shown, just generating code at compile time and then inserting that into the queue to be compiled. And you could imagine a whole metaprogramming facility built around that. And there will be one, but that style of metaprogramming also has some drawbacks. It has some benefits. It's very good for looking at your program as a whole entity, but issues with it are things like, oh, I'm generating some code, and the place that generates the code is very far from the place that's using the code, both in time and in space in terms of where in the program those two things are. And so I wanted to also provide a kind of metaprogramming that's not really for whole program things, that's for individual function kinds of things, that's maybe for quick and light kinds of tasks, right? So that's what we're going to talk about today. And what we're going to be talking about today is procedural polymorphism, right? We're not going to do data structures because it's a whole just doing procedures was a big enough implementation milestone, and there's going to be tons and tons to talk about just with procedures. We'll do data structures next time, hopefully. Now, when I say polymorphism, I just mean procedures that can compile to different versions based on what arguments you pass or how you configure them, right? It's just like template functions in C++. I don't really like to say templates because the word template, as far as I'm concerned, has been uglified. Like, it reminds me, when I say template, it reminds me of all the horrible things about C++. So I didn't want to do that. I don't like to say generics, because the word generic in English has mostly negative connotations. It means bland or boring or featureless. C++ is amazing because every single name in C++ is either wrong or has negative connotations. So generics is one of those. So I figured, well, I'll go to the sort of name for this that comes from the functional language world, which is polymorphism. Right, and it's cooler, right? Polymorphism is what you do to get cool magic items in NetHack, so it's got to be good. So let's just get started and see what happens. As always, I've got this main routine that I'm going to be working my way through and uncommenting parts of the program bit by bit. And we're going to start with this routine basics to show the basics. And let's run it. As usual, we're just printing out a lot of different interesting things. And let's look at how we are printing these things out. So I'm starting, I've got this routine called PrintNumber, and it takes an argument called number, and instead of a type here, I'm saying $T. And what the $sign indicates is that this is a type variable, which means we don't know what type it is at declaration time. The type of this variable will be determined when the function is called. Because we're being very low rent, we're going to do this thing in printf where we print the same variable as both an int and a float and just see how it comes out. You're not really supposed to do that, but it's good enough for current purposes. We pass any number of arguments, or one argument, but of any number of types. So we're declaring n1, n2, n3, n4, and n5, all of different types. And they have the values 1, 2, 3, 4, and 5. And we're just calling PrintNumber 5 times. And let's just see what that says, right? So this is the very top of our output, PrintNumber, and the first three are integer types, right, of an int, a U8, and S64, and so those are ending up printing successfully here from this %d, and the last two are floating point types, right, and so those are coming out the second time. So the printf part here is not supposed to be interesting, but what's interesting is we've called the same number with ints and floats, and this is basically the same as you would have in C++ templates, right? No surprise yet. Except we've got a much lighter weight syntax of declaring it. Instead of saying template, blah, 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 argument list, and whatever, you just put this $sign, right? It's a one character difference. All right, let's go to a slightly more involved thing. I've got this function add, right, that takes two arguments, p and q, and returns something, and the thing it returns is the same type as p, and q is the same type as p. Now, we only do the $sign once. We'll talk about why in a minute. Anyway, so the body of this function is just, we make this new variable x that's p plus q, and we return x, right? So we're going to call this a couple times. First, we're calling it with two integers, 5 and 3, and then we're printing the result. And then we're going to call it with 1.1 and 2.2 and print the result. And you can see it worked both times, 8 and 3.3. Now, the reason that we only use the $sign once is that the $sign tells us which argument is authoritative over what the type should be, so that when we give an error message, the error message says the right person is wrong. And for a function like add, it doesn't really matter because it's a symmetric function. The two types don't matter. But later on, we'll be looking at some things where it makes a lot of sense to do that. So here, I'm going to uncomment this thing that calls this function erroneously with an int and a float. So we don't automatically coerce between int and float. So that should complain. Let me get it at the top of the screen. Right, so we get number mismatch, integer versus float, checking argument 2 of call to add. We wanted to assign 32, and we were given a float for argument 2. If I change where this $sign is, if I put it on the q, and I do the same thing again, now it's complaining about argument 1, right? It's saying argument 1 doesn't match argument 2. So that's what the $sign means. And again, we'll see some versions where that really matters in a bit. But the point to make is you define one of these just like any function. And there are no headers in this language, right? So you don't run into any of the header-only programming problems like in C++. As you start using templates more and more, your headers become gigantic and your CPP files become small, and that really bloats your compile time and it makes your program hard to understand. We don't have any of those issues. So I can move this function anywhere, right? I can take this add function, I can drop it at the end of the file, right? And that still works, right? We're still adding. I can even put it in a different file. I can say load foo, right? And I'll put it in that file and it still works, right? And just to prove that it's actually working, right? If I comment out that load, we don't know what add is, right? So that's all great. Now let me go put that back. All right, so now that t is not just a type variable that takes over the whole type. You can pattern match against a piece of a subtype. So here we made a swap function that'll work on anything. You pass a pointer to each thing. A is some type and B is the same type. And we make a temp variable that takes the star A. Star is a dereference right now. That syntax may change in the future, but it's a dereference just like it is in C or C++. So we're making a new variable temp that's a copy of whatever's in A. We're assigning A to whatever's in B, and we're assigning B to what's in temp. Classic swap, but it'll work on everything, right? So here we're saying, okay, some A and B are 3.5. We're going to print them out pre-swap. We're going to swap them. We're going to print it out post-swap, right? So here's what we get, 3.5, 5.3. We're doing it with two strings, hello and sailor. We swap them and print them, hello sailor, sailor hello. And we're even doing it with a bigger struct, right? It's pretty easy in C or C++ without even going to templates to build a swap for like pointer size things or whatever. And just casting to void star, but you know, we can do it on bigger stuff. So here's two vector 3s. One of them is 149, one of them is 246. And we're going to print it out pre and post swap. And again, we see 149, 246, and then 246, 149. So that's a very handy function to have. And it's not a macro. You know, in C, you would have to do this as a macro. But here, we actually get good type checking on it as you pass the arguments in. And it's just regular code. Are people still complaining about the audio? Like what? Anyway, Okay, now I didn't want to do a reference kind of thing like in C++ because I like knowing when things can be modified. So I didn't make a reference type. So you need to pass pointers to things. If you don't pass pointers, it'll complain, right? Because the swap function says A is a pointer to some type T and B is a pointer to that same type. So if I just pass these two things in as vector, it'll complain. There's a type mismatch, pointer versus non-pointer, when trying to match polymorph argument 1 of swap, right? So it gives you a very useful and understandable error message in that case. Let's go to another compound type. Sum, right, which here we're going to take an array of some type, right? So the brackets means it's an array, and then this is what type it's an array of, which is anything. And we're going to return that same thing, and we're going to make a new variable called result of the type of the array element, right? And we can actually omit the equal 0 if we want, because 0 is the default value for anything anyway. We're going to say for every element of the array, add it to the result, and then we're going to return the result, right? So this is a function that will sum over an array of any type, as long as that type supports plus equals, right? So now we're going to come down here and we're going to make arrays of a few things. Here's an array of ints, an array of floats, an array of unsigned 8 bits, an array of float 64s, which is double in C or C++. And we're going to print the results. And here you see those results, 1262, 6.6, 17, and 5308, which you can confirm if you pause and screenshot that that's all correct. This number, however, is maybe not correct or maybe seems a little low. It's because we've got unsigned 8-bit numbers, which means we're returning an unsigned 8-bit number, which means that when we add these up, we're going to overflow, which is an interesting situation to be in. And we'll come back to that later because that kind of thing is a motivation for one of the features that we will have before too long here. Okay, so here's another use of a slightly more complex pattern match on a type. We can make a function add to array. If you've watched the previous streams, I've always had to apologize, like, oh, here I'm adding something to a dynamic array, but we don't have like parameterized types yet, so it's you know, it's I have to do all this ugly casting and stuff. Well, I don't have to do that ugly casting anymore. So here I can say add to an array. First we take a pointer to an array of arbitrary type and then some item, and then we can call the standard library function that basically takes void pointers and the size, right? And I don't have to indicate the size manually and whatnot. So let me just show you. If I go into basic, this is what we're calling, which is sort of this system function that just takes void pointers. So what this is a type safe check around those void pointers. And that's actually, I've defined this function here called add to array, but the system function is exactly the same. I've got an array add that I use everywhere else that just calls that, right? And now this size of is computed at compile time, whereas for dynamic arrays in previous demos, it was actually stored in the array, which is a little bit inefficient, right? Because you're taking storage for that size. Now I don't need to take storage for that size, right? It gets computed every time you call add to array or a similar function. All right, so here's a demo of that. So we've got an array of strings this time. We're adding 4 strings, hello, sailor, radio, and brain, to the array. And for everything in the array, we're going to print that string. So here's also the integer index, right? So we've got 0, hello, 1, sailor, 2, radio, 3, brain. And then we're going to write a find function, right? So here's find an array of any type and an item of that same type. And we're returning a signed 64-bit index into the array. It's just signed 64 just because it might be a really big number. And I don't like to use unsigned unless there's really a reason for it, because signed is more natural, I think. We'll see. That's a whole discussion that can happen some other time. But anyway, So how do we do that? Well, for everything in the array, if the thing we're looking at is that item, return the index, otherwise return -1 that we didn't find. Oh, that's the other reason to return an S64 is you can do -1 if you're not found. Alternately, you could do a second return value, right, if you wanted to, because we have multiple return values, as you may have seen last time. We'll be using those again pretty soon. So this find function will work on anything that double equals works on, right? So double equals happens to work correctly on strings now, unlike in C and C++, right, on native strings. So I can call find on this string sailor, and it prints out the index, and that index is 1, right? And you might think, oh, well, in C, maybe this string is interned, so the pointers are the same. So this would work anyway, because a C compiler will optimize and repoint things to the same string if they're constants like this. So instead of doing that, I can do this version where I'm dynamically concatenating this string from say and ler and an exclamation point by calling this mprintf function. And if I do that same thing, it still works. Index is 1, right? So that's all great. So those are just some very simple examples of how you can very quickly define functions that work on anything and get good error messages. Like error messages are important because they're your user interface to day-to-day programming. So it's important that those be good. So, okay, right, I mentioned that the $ position is important and it can be helpful when decoding error message, right? Because there's an authoritative idea of who's right. So if you're going to find something in an array, it makes sense that the array determines the type of the thing you're looking for, right? And then if you pass in an argument, well, it's the argument that might be wrong. If you've got an array of strings, for example, and you pass an integer to find, then the integer is wrong, right? And so we get an error message that tells us that. If I run now, it says, hey, type mismatch. Checking argument 2 of call to find, we wanted a string, but we were given an integer of unspecified size, right? Because 72 could be of any size. So this is really good, right? Because we could be dealing with a function that takes many types, right? Here we're just taking one type, but we could be taking multiple types, and it's very good if the error message can tell us exactly which types are wrong, rather than saying, oh, vaguely we couldn't resolve this template match, here are all the possibilities, or whatever. Now that gets more complex when we have function overloading later on, which we don't yet, but this will still give us a way to be concrete and reasonable and communicative about what's going on. So let's go on to another couple tests. Here's a silly function called xy_test, which takes some type, and we just print out the x and y coordinates of it. And we're going to give it vector 2, vector 3, and vector 4. And let me go show you what the definitions of those are, because they're going to come back through the rest of the demo. I've basically given them silly values by default just so that we can see what the function is doing by the contents, right? So the whole number part of a vector 2 is 2, the whole number part of a vector 3 is 3, and a whole number part of a vector 4 is 4. So that's how you know what type the function's operating on. And then the xy part is 0, 1, 2, or 3 based on which component it is. And then, just to be sly, I've swizzled the components of vector 4 so that the x and y are at a different memory offset than they are for vector 2 and 3, and we'll show why in a second. So anyway, let's come back down to that. So we've got our xy test that's just printing the x and y of whatever we pass it, and we're going to call it on vector 2, vector 3, and vector 4 first. And we can see that output, right? So 2.0, 2.1, 3.0, 3.1, 4.0, 4.1, just like we expect, right? Now, because we use dot for both value and pointer dereference of a struct, we can use that same code on pointers and it still makes sense. So I can pass a pointer to a vector 2, pointer to a vector 3, or a pointer to a vector 4, and I get the same results, right? 2.0, 2.1, 3.0, 3.1, 4.0, 4.1. Same as right here. Now, let's do something with a little bit even more of a complex type matching. I've got a function here called do 3 times. It takes a function and an argument, and it calls the function on the argument 3 times. That's what for 1 to 3 does, right? So I'm going to make this function square in print, which takes a vector 3. It's going to square the components of the vector 3. It takes a pointer to a vector 3. It's going to square the components of the vector 3 and print it. And because we're calling this 3 times and we're modifying the memory of that vector 3, we're going to repeatedly square the values. So the vector is going to get bigger and bigger, right? So here we've got a vector 3. We're overriding the default values. We've got 1.1, 10, and 0.5. And now we're calling do 3 times square and print. And so that's what's happening here is first v is 1.21, 100, and 0.25, which is the squares of all these numbers. And then it's the squares of those and the squares of those. So that's sort of the very basics of how this stuff works. And now we're going to go on to some other things. First, we're just going to look at some error messages. We've already done a couple, but we're going to go a little further into what happens in slightly more complex situations. Because again, error messages are important. So here, I've got a function called multiply and add with constants. We have a value, or a parameter a of some type t of a, right? Ta, I've just called that. And b, which is always a float 64, and we're always returning a float 64. And we're going to return 1.5 times a plus 4.6 times b, right? And we're just going to, let's run that. So we're printing that out on K1 and K2, and the result is 7.6, right? Or K2 and K1, because we're multiplying by different constants, right? So that's fine, but now we're going to make another polymorphic function that calls this one, right, to set up this multi-layer situation. We've got another function called doMathThings that takes a parameter a and b of different types and returns the type of b, and we're going to call multiply and add with constants on a and b, right? And then we're going to pass it 1 and 3, and then we get this result, right? So that's fine, but now what happens if we get a type wrong, right? Let's say x is float 32 instead of float 64. What happens? We get this number precision mismatch. We wanted 32 bits, but we got 64 bits. In binary operator plus, on line 366, right? The left type of plus was float 32. The right type of plus was float 64. And that happened during the polymorph of multiply and add with constants, which is what at line 382. And that happened during the polymorph of doMathThings, which was at line 388. And by the way, in multiply and add with constants, right, TA, this type variable was float 32, and in this doMathThings, TA was float 32 and TB was float 64. So it gives you these things in a very digestible manner that's kind of easy to look at and understand what's going on, as opposed to some compilers which just sort of spew stuff at you, right? So that's nice. So now let's do something, let's try some various permutations of this. If we pass x as a float 64 and y as a float 32, we get a different error, potential loss of information in return type, right, for return value 1 of doMathThings, right? And the reason is just that we're trying to return a float 64. Multiply and add with constants returns a float 64, right? So now we're trying to return that, but we said that our return type is TB, which is float 32, right? So that's no good. And if we do both of them, then we still get an error message, right? For the same reason, actually. Anytime TB is float 32, we're going to get an error. So this is actually not a very good chain of functions to put together. And the reason is this one is insufficiently versatile. Because it always wants to return float 64, then basically the outcome is that both of these always have to be float 64. But the point of this wasn't to make smart functions. It was to show error messages and diagnostics. So now let's call doMathThings and pass it a vector 4. And again, now we're saying, okay, well, the parameters to multiply and add with constants were not good, right? We wanted to float 64, and we were given a pointer to a vector 4, and that's what TA and TB were, right? Very easy to understand. Here's one. See if you can tell what's wrong with this function before I run it. What happened is I used a $sign twice, and it catches that. It says, oh, t was already declared as a polymorphic variable, right? In line 403, I tried to use a $sign, but here it is in line 402, which is, it's helpful to have those two locations if the function's much bigger and you don't know what's going on, right? So if you mistakenly put the $sign, it's fine. You'll catch it. Oh, now, right. Now I'm passing an integer, but I'm trying to assign it to a float. And now finally it works, right? So usable all the time. So again, we have add to array. Let's make incorrect calls to it with different versions. So I've got an array of vector 3s, and I'm passing a vector 2. And again, in this first version where the $sign is on the array, saying the array is authoritative over the type, it says I wanted a vector 3 but got a vector 2 in the second argument, and that's no good, right? If we switch the $sign to the second version, then it'll complain that the array is wrong, right? I wanted a vector 2 but was given a vector 3 in argument 1, right? I wanted an array or a pointer to a dynamic array of vector 2. I was given a pointer to a dynamic array of vector 3. And if you put $signs on both, you'll get the same error as what we just got. Hey, t is already declared as a polymorphic variable. So that's all good. Now that we've seen error messages, let's look at some new features that are going to build more and more to interestingness. All right. Baking. Here we've got a function called usingTest, and we're using the first parameter, right? Remember that using lets us refer to these components as which, it's like a this pointer, right? But it can be anything, right? So this is sort of verifying that that still works with polymorphic types. I'm going to pass different vectors of different types in here, and we're going to get you know what? I forgot to do something. I skipped part of my demo because it was a comment. Hold on. Let's talk about classical problems that happen in C++ and other languages that have compile time code generation like this. One of them is error messages, which we just covered. And the other problem that often happens is code bloat. Well, the third one is compile time speed, which we will suffer from greatly less than C++ for various reasons, partially the lack of header files and partially that our compiler is just going to be better about this. Partially that our compilation model is not about compiling a bunch of independent units and then putting them together, because that means you have to generate the code all these times, right? We're compiling as much as we can at once, and what that means is that we don't ever generate the code for a particular instantiation of a polymorphic function more than once, right? And I will actually, what I'm going to do is I'm going to unleash the whole program here so that all these functions, even the ones we have yet to see, are going to run, right? So now we're doing a whole bunch of stuff. And we're going to go now to another file that is going to be a little bit of a meta file and load this program in a way that gives us diagnostics over which polymorphic procedures are generating new code and which ones aren't, right? So I've got this file here called demo Polyprebuild, and what this is just a build function that controls build settings over what we want to see. And the reason this is in a different file is because we're going to start up building this file, and because we don't have ordered compilation, we want to be sure that any settings that we set take effect before any of our main program is compiled, right? And that's true whether you want diagnostics or like if you want to set the size of the target architecture or something like that, right? You want to make sure that you set that stuff before you're actually compiling anything. And so what we do is we compile in the compiler this build function right now, which is mostly commented out, but we're going to uncomment various pieces. The build function sets some build options, which right now is just this. We say we want info flags if polymorph match. And then we're going to update the build options, and then we're going to add demo.jai, which is this other file that we were just doing, right? So what that's going to do, I will show you right now. Demo Polyprebuild pipe more. So as the compiler builds all these polymorphic calls, it's going to check, and if it matches one that's already generated, it'll tell us, right? That's what this flag does. And we can see, for example, that there are lots of instances of things matching stuff that already was compiled. And we can go look at a couple of them matched. So for example, line 241, you know, all these array adds, I called array add 4 times with the same types, right? And that generated the same code for the bottom 3, right? So line 241, 242, and 243 all generated the same code as 240, right? So we see that here. 241, 242, 243 all generate the same code as 240. Let's look at another one. You know, 268 generates the same code as 267. That's no surprise. Let's find a couple that are far apart. Here, let's find 2 that are in different files, if we can do that. Oh, maybe I don't have it. Oh no, that's the other diagnostic as well. All right, you get the idea. Is there one? Okay, I want one that's far apart. I want one that's far apart. Well, here's one. Okay, line 769 to line 731. Right. Let's see what that is. Oh, this is more complicated. We'll get to that. Okay, but let me show you the other thing. Okay, so that was detection of, hey, you're calling this polymorphic function with the same type, so we don't need to generate it, right? Now, there's another thing you can do, which is maybe you're calling a function with different types, but the output from those different types is actually the same code. Then we can map to the same function, even though the type signatures of that function is actually different, right? And we catch that in a few cases. It doesn't happen that often, mainly because the regular type signature polymorph match, where the types of the arguments all match the same, catches most cases. But we can turn on this info flag to tell us what do you deduplicate. And this is the thing I was confused about that I expected to see. All right, so for example, line 332, a procedure duplicate was detected and mapped to code generated at line 331. Well, what was that? Line 332, this is the thing I was talking about, where there's a vector 3 of XY test. It's saying this is the same as line 331, which is this. But they're different types, right? One's a pointer to a vector 3, one's a pointer to a vector 2, but the offsets of x and y in a vector 2 are the same as the offsets in vector 3. Now note that we didn't get that for the vector 4, and the reason we didn't get it for the vector 4 is because I swizzled the vector 4, right, in order to make this not work. But if I now go in and unswizzle it so that x, y, z, w go in the right order, right, and then go back to line 330, whatever, where this stuff was, now I will rerun, and we should see, there we go. 333 is now the same as 331 as well. So anytime we generate a variant of the code for a particular polymorphic function, we then go back and search the other things we generated to see if they match. And we do that in bytecode before we generate platform-specific machine code, so the platform level doesn't need to know about this. We've got one more where we're detecting duplicates across different files, right? So that was another thing I wanted to show. So in pool, which is a memory allocator that we'll look at in a little bit, right, we're calling array add on an array of pointers to memory blocks, right? But pointers are always the same size, so that's the same code as that generated in demo line 240, where we are adding, actually float 64s, which is interesting. Actually, that's probably a case where we have to make that not match. depending on the calling convention of your architecture, you know. For the bytecode, a pointer and a float64 are the same size. On some architectures, you might use floating point registers to pass things. So that's a little thing that you know, may be different in different platforms. But the point being, you can detect the same thing happening in multiple places. So, for example, anywhere that I was going to add a pointer of things to an array, you get the same code. All right. So now let's go back to what I was being overzealous in trying to demo, which was baking. Let's do baking later. There we go. So we're just running the demo now. Baking. What is that? Well, okay, we've got this using test function, and like I said, we're using this parameter, and that's kind of like it's a this pointer, so we can just say x and y without saying a.x and a.y, and we're just printing the coordinates, right? And we're just going to call that first, just like we have been. So just show, look, it's a polymorphic function. You're used to that now. No problem. So we get this. A.x is 2.0, A.y is 2.1. So instead of calling it, I can do a thing called bake, where I use this bake directive to generate a compiled function. This doesn't happen at runtime, right? This is a thing that happens at compile time only because we're a compiled language, right? So I'm going to bake a version of this function where the type t, the type variable t in the header, means vector3, right? So I'm going to bind that to this name baked3, and from now on I can use a non-polymorphic function. It's been like solidified where the types are determined. So now I can make a vector3 and call baked3 on it, right? I can bake another version for vector2 and call baked2 on a vector2, right? Now, of course, whoops, if I take a vector4 and I try to call baked3 on it, well, that's baked for a different type, so that's going to give me an error, right? Type mismatch. I wanted a vector3, but you gave me a vector4. So that's all cool. All right. Now, so far, I've just been using bake to do things you can do anyway by calling something normally, but sometimes you may not be able to specify types by calling a function. For example, here's a weird random function that doesn't take any parameters, but it's got a return type that's a type variable. And how do you do that? You can't specify that return type just by calling the function. But what you can do is you can bake it in different ways, right? This is not a very good random number generator. Don't use this at home. But we're taking a large value, cafe babe food face, right? And we're going to cast that value to the resulting type and return that as our random number, all right? So the first thing to note is, like I said, you can't call this function directly because it won't know what t is. So if I just try to call random like that, it'll say, polymorphic variable t is needed but was not specified on line 499. And by the way, on line 492, here's the procedure needing the variable. Okay, so that's very helpful. It gives you both the calling site and the site where the variable lives. But I can bake that for different types. So I can bake a random that returns an S32, right, a signed 32-bit number. I can bake a random that returns an unsigned 8-bit number. So now I'm just going to call those, and I'm going to print the result in decimal and hex, right? Just so you can see it. And that's up here. A random of S32 gives me food face, or this negative number, right? And random of U8 gives me 206, or the CE, the SK at the end of food face. So that's cool. Hopefully that's clear how that works. So now we can bake something with multiple types to just show some more complicated cases. So I've got a named bake test where I've got A1 and A2 that are both of type A. I've got B1 and B2 that are both of type B, and I'm returning an A and a B. For the return value of A type, I'm going to sum A1 and A2. And for the second return value, I'm going to take the product of B1 and B2, right? So I'm returning A sum and B product. So I can bake that in different ways, right? So here I'm going to bake it with A being float and B being int, right? And then I'm going to call it down here. Sum is whatever, product is whatever. I'm passing it these literals that can implicitly cast to either int or float, right? That's the rule for literals. If you type a 4, that could be a float, right? So unless you specify that it's not. So here we go. We're printing sum and product, right? And sum is 3.0, product is 12 because we baked it with A is float and B is int, right? Now we can we can swap that, for example. B is float and A is int. And now we'll get, oh, no, because the printf expects them in the opposite order, so let's not do that. Right, that worked. It's just that the printf then is trying to print a decimal in this %f and a float in the %d, and that's bad news for both things. But it worked. So we can do this other thing, right? Note that we're baking with named arguments, so we can specify the arguments in any order, just like with regular function calls, as we saw last time. So we can bake with b is int and a is float, which is the same types we just baked, but I'm just specifying them differently, and that does what you would expect as well. Now we can have this weird function where there's no type on the outside at all. It's not in there's no type variable in the arguments. There's no type variable in the returns. But internally, we're just doing something that uses some random type, right? And we can bake that. We can bake this function internal with some type as U64, and we're going to call it on 6000 and say, hey, that's 6000. And just like with before, we can't really call it directly. If we try to do that, it'll complain that some type is needed but was not specified, right? And there it is. Line 538 has some type. Okay. Now let's start getting to the, that was the intro. That's the intro. And now we're going to start getting to the kind of the really interesting feature that gives this language a lot of new things, or at least certainly things that I haven't seen before. All right. Here's modify. Now, so far, what I've just shown is, here's the basic mechanism for polymorphic functions in this language, equivalent to template functions in C++ or D or something. Now, a lot of languages that have type variables and polymorphic functions then start layering on things in the language to help you deal with the complexity of that, right? Like in C++, for example, there's this proposal called concepts that's about trying to make error messages easier to catch, or trying to make code more self-documenting, that's about describing what the parameters to a polymorphic function could be. I don't like that approach, because you start layering this declarative language on top of your imperative language, and you're making the language more and more complicated. So just like in that first demo where I said, hey, compile time execution lets you do all this awesome stuff, now the philosophy for the rest of this demo is going to be to leverage compile time execution to the greatest extent possible in a way that other languages don't do. And that gives us a great degree of amplified power over these generic template polymorphic functions, right? So now let's start looking at that. So we're going to look at this thing called a modify directive. And what that is you can attach it onto a polymorphic procedure, right? And it supplies code that runs at compile time that maps the types given by the user onto the types of the generated function, right? Prior till now, anytime we had a polymorphic function, the type of the resulting function that gets compiled was whatever the exact type happened to be at the calling site, right? And now what the modify directive is it takes a function that can modify that type and turn it into a different type. And to do that, we're going to use the runtime type information that we provided earlier. And if you didn't see that demo, it's a couple demos ago. You can find it on YouTube. But basically, we have these type info structures that are generated by the compiler and put into a global table, and we can use them to reason about types, right? Now, here, we're not going to do that at runtime. We're going to do it at compile time, but it's the same mechanism, and it's very powerful. So as our first test, we're going to be very boring. We're going to take some variable a that's of any type, I don't know, right? And not an any type, which is a different thing we demoed. This is of arbitrary type. It's anything that you could pass. And then we're going to modify it by this function that takes that type t as a pointer to a type info and returns whatever it wants. And it's going to ignore the initial value of t and say, you know what, the type of this parameter should be a signed 64-bit number, right? So now we're going to call it with an int and an unsigned 8 and a signed 64, just like we did at the beginning of this demo. But what this modify is going to do is override all those choices. So in here, we're printfing the value of a, and the size of a is some number of bits, right? And then we're going to print the pointer value of this type info so that we can verify that it's the same every time, right? Now, to tell you the size in bits, we're going to cast the type info to a type info integer, which would be a dangerous thing to do usually, but we know down here we're only calling it with int, so it's fine. And then we're going to look at this field size in bits that's on that type info, right? And what we see when we run this, hopefully I did everything right. Here we go. Value of a is 5, but the size is 64 bits, and here's the pointer to the type info, right? Value of a is 4, but the size is 64 bits, and the value is minus whatever, but the size is 64 bits. And here's the type info every time. So that's interesting, right? We've obviously got control over what gets generated here. Now, this is a very trivial case. But we're going to start building it into more and more complex things. So now, just to show you that that's working, I'm going to turn off this modify directive, but just by commenting it out. So now we've just got a regular function in test, just like we did through all those examples, right? And now if I run this again, you'll see the first one's 32 bits, the second one's 8 bits, the third one is 64 bits, just like you would expect, right? So obviously, oh, and the type info pointers are all different because those arguments are different types. So it's still a polymorphic function, it's just this modify is overriding it to do the same thing every time we call it. But we can do things that are more interesting than that, okay? So remember that random function that we couldn't call directly because the return value is only specified here, so we were baking it before. It's still got Cafe Babe food face and is still casting that to some type t. But now we're providing a modify function, and it's saying, well, if t is null, which is what happens when this type wasn't specified, then let's just say we're making a signed 32-bit random function, right? Or random number, right? Otherwise, return whatever type was specified. So we can now call it. We couldn't do this before, right? But now we can call it directly, and by default, we'll get a random that gives us a signed 32-bit number, right? Which is that stuff. And just like before, we can bake it to U8 and call it, right? So now we've got a very versatile function. We can call it, or we can specify what we want and call the specified version. So that's cool. And just to show that that's doing stuff, here let's change the default value to U16 instead of S32, and we'll run it again. And there we go. We have an unsigned 16-bit number instead of a signed 32-bit number, right? So that's great. Let's go back to our sum example, right? Remember last time I summed together all these elements of an array. But now I want to be more careful about what I'm doing. Because remember, when we summed the array of 8-bit elements, if you returned an 8-bit element, you're going to overflow very easily. I want to avoid that. But I also want my sum function to work on all kinds of types. So here's what I'm going to do. I'm going to return a different type. So now I'm taking an array of t, but I'm returning an r. What's r? We'll find out, right? You can't specify this by calling, so our modify proc has to specify it. And what does it do? Well, it takes t and r as arguments, and it returns two return values. And first of all, we're going to say, hey, if t is not an integer, then just return whatever t was, both for t and r. So, for example, if you call sum on an array of float 32s, then float 32 is fine. We're just going to sum up a bunch of float 32s, and that's great. Floats have enough precision. We're only worried about integers. So right away, this sum will work for any float type and do exactly what the previous sum did because we're not monkeying with the types. Okay, down here we know it's an integer, so let's look at the type info, size in bits. If it's a 32-bit integer or greater, signed or unsigned, we're not specifying, then again, return the same type for both T and R, right? So if it's big enough, for the purposes of however we're going to use this function, we've decided 32 bits is big enough, so just do whatever, right? But suppose you passed it a smaller number than that, like 16 or 8 bits, then we want to return, let's say, 32 bits. We always want to make sure it's at least 32 bits. But if you gave us an array of signed things, we'll give you a signed 32-bit. And if you gave us an array of unsigned things, we'll give you an unsigned 32-bit, right? So if it's signed, we always return T in all these cases, right? Because it's an array of T. You don't want to monkey with that. But our return type is going to be either signed 32 or unsigned 32, depending on what the type of the element of the array was. That is a very specific thing that we just did, and very complicated. And if you're trying to do that in a declarative way, it's going to get messy and going to require this big meta system with all these different ways of saying things. But we just leveraged the programming language that we already have to do this very complicated thing, right? So now here's the actual body of sum. Once again, we just got a result. We say for A, add it to the result, and then return result, right? So now down here, we've got 3 arrays of different types. They're starting uninitialized, which is what that means, if you recall that from a very early demo. We're filling the arrays with, at every index, we're putting that index times 10, but of different types, right? So the first array is going to be float 64s, U16s, and S8s. We're going to sum them all, and we're going to print the sums, and that's what we get here, 450 for all 3 of these. Now, notice that this is really working, because 450 is not storable in 8 bits, right? But our third array is an array of signed 8-bit numbers. So obviously the return type for C is bigger than 8 bits, right? Whereas before that would have failed. Now our modify proc has made it succeed. So that is, to my mind, a very powerful thing. And I'm going to take 1 second and eat a bite of cupcake before going on, because I'm getting hungry. Pardon me. This is the advantage of doing a demo from home rather than at a conference.